Hey everyone, and welcome to another Explainer. Today we're going to completely pull back the curtain on a truly fascinating piece of everyday technology. We're exploring a literal invisible superpower working behind the scenes on your device right this very second. Memory management. Seriously, it's amazing. Let's just dive right in.
So I want you to think about a super relatable, everyday problem. How exactly does your computer or even your smartphone smoothly run a dozen massive applications all at the same time? You know, your web browser with 50 tabs open, your music playing, your messaging apps, a heavy photo editor, all running flawlessly when you only have a relatively small amount of physical RAM actually installed. It kind of feels like a magic trick, doesn't it? Well, today, we're going to learn exactly how that trick is pulled off. To set the stage for this, let's take a look at a really thoughtful quote from the ancient Roman educator Quintilian. He said, "Nothing is so much strengthened by practice or weakened by neglect as memory." Now, obviously, he was talking about the human mind, but honestly, this perfectly applies to our modern machines too. Operating systems are constantly practicing, managing, and optimizing their memory allocation schemes, just so nothing gets neglected and your performance stays lightning fast. Here is our quick roadmap for today's Explainer. We'll start with an intro to memory management, cover paged memory and virtual memory, look at the threat of thrashing, hit some real-world apps, and wrap up with key takeaways. Starting off with Section 1, Intro to Memory Management. The entire foundation of how modern operating systems handle storage revolves around this one incredible breakthrough concept: virtual memory. By definition, this is a technique that lets programs be executed even though they aren't stored entirely in your main memory. Think about that for a second. It completely removes the restrictions on maximum program size. It gives you the appearance, the total illusion of vast amounts of physical memory when, in reality, your physical hardware is pretty strictly limited. Moving into Section 2, Core Concepts, Paged Memory Allocation. Let's cleanly break down the core architecture here, because there are really just three vital terms you need to understand. First up, we've got pages. These are fixed size blocks of a program's logical memory. Basically, just think of it as dividing a software job into totally equal chunks. Second, we have frames. Now, these are the fixed-sized blocks of your actual physical memory, your physical RAM. Crucially, the size of a frame is always exactly equal to the size of a page, ensuring everything aligns perfectly. And third, the page table. This is the essential data structure that maps the logical page number directly over to the physical frame number in your RAM. To actually see this concept in action, take Job 1 as an example. Say it's a 350-byte program divided into 100-byte pages, page 0, 1, 2, and 3. When mapping to main memory, page 0 might go to frame 8, while page 1 goes to frame 10. They are completely out of order. This is huge because it means memory doesn't need to be contiguous anymore. But there's a slight catch. If you look at page 3, it only has 50 bytes of data sitting in a 100-byte page. That remaining 50 bytes? It's wasted space. We call this tiny downside internal fragmentation. Section 3. Core Concepts, Virtual Memory and Demand Paging. Think about when you open up a massive piece of software. With a process called demand paging, the operating system doesn't just awkwardly dump the whole application into RAM all at once. No way. It only grabs the highly specific modules you immediately need exactly when they are requested. So if you never click on the Help menu, the code for the Help menu is literally never moved into memory. It saves an absolutely tremendous amount of space. But wait, what actually happens when you finally do click that Help menu and the code isn't in your RAM yet? Well, it triggers this lightning-fast, fascinating sequence of cooperation between your hardware and software. Step 1, a page fault is issued. This is basically a quick system alert shouting, "Hey, we need data that isn't here." Step 2, the memory manager jumps into action and finds an available page frame in physical memory. Step 3, it loads that requested page right from your secondary storage into the frame. And finally, Step 4, it updates the memory map table, or MMT, and the page map tables, the PMTs, so the system knows exactly where to find it next time. It is also briefly worth noting that virtual memory can be implemented using two totally different mathematical approaches: paging, which we just walked through, and segmentation. Like we saw a moment ago, paging allows for internal fragmentation. That's the wasted space inside a frame, but no external fragmentation. Segmentation is actually the exact opposite. It doesn't allow internal fragmentation, but it does allow external fragmentation. Operating systems just have to choose between these based on how they prefer to manage the empty spaces between our data. Section 4. The Threat of Thrashing. Okay, to truly understand the limits of this system, let's use a super relatable analogy. Imagine your physical RAM is your bedroom dresser, and your secondary storage is a storage closet way down the hall. If the weather keeps changing wildly all day, you might find yourself trekking back and forth to that storage closet every 5 minutes just to swap out sweaters. What guarantee do you even have that the sweater you just put away isn't the exact same one you'll need 2 minutes from now? If you do this too much, you spend literally all your time walking back and forth and absolutely no time actually enjoying your day.
In computer science, this frustrating scenario is formally known as thrashing. It's a phenomenon where there is an excessive amount of page swapping going back and forth between your main memory and your secondary storage. It results in incredibly high overhead, and almost no useful work is actually getting done. This right here is exactly why your computer sometimes completely freezes up when you have way too many massive apps or a million browser tabs open all at once. The system is just frantically running back and forth to the storage closet.
Section 5. Real-world applications.
Now, fortunately, modern operating systems are really good at avoiding thrashing, which brings us to the real-world advantages of virtual memory management. First off, it allows for a theoretically unlimited amount of multi-programming. You can just run dozens of jobs at once. Second, most programs actually spend a huge amount of time just waiting for you to type something or waiting for a file to download. With virtual memory, that wait time is never wasted. The CPU simply pivots to another job that already has its pages loaded up. Plus, it lets different programs seamlessly share the exact same background code and data, and it allows massive software systems to be built independently in separate pieces and then linked together later. It's a total game changer.
And finally, Section 6, Summary and Key Takeaways. Let's quickly lock all this information in with a rapid-fire review. Here are your absolute core takeaways from today. Always remember that logical pages from your software fit perfectly into physical frames in your RAM. Remember that demand paging is the super efficient process of only loading the exact data you've just requested right when you request it. Because of this, virtual memory creates the flawless illusion of limitless space, completely unbinding us from our physical hardware limits. But always be aware of the danger of thrashing, that dreaded system-freezing state of excessive data swapping.
I want to leave you with a somewhat provocative thought to ponder. As you sit there right now, watching your screen, running the web browser or the app that's playing this explainer, how much virtual memory is your own device actively swapping back and forth at this exact moment? Flawlessly, completely behind the scenes, without you ever even noticing. It truly is a kind of technological magic. Thank you so much for learning with me today. Stay curious, and I'll catch you in the next explainer.